this computer. I have to go get a plug at some point. Place here.
I'll be alone.
Huh?
I said, I hope I'm not the only one.
Oh, you're gonna be the only one. Are you kidding me? Haven't you seen the faces of like of hopelessness on everyone's, you know,
Well,
like
I have that face too.
I
that's
know
why I'm
everyone's
here.
hopeless. See, Nathan, well, okay, Nathan's here. I've got someone online. But there's this is a desperate hour for everybody. I feel really bad. But what am I gonna do? What can I do? I'm trying to teach it. Mistakes were made. Algebra was invented. I actually have been starting to look for books on like applied abstract algebra, because I'm so worried that, like, I'm actually really worried that people are gonna like not want to learn this. I mean, there's push from everybody.
Isn't that just 511? Is it 511 the applied track?
No, 511 is it's what they teach for more for the math ed level. Yeah, I don't know. Anyway, sorry, Nathan, just give me a second. I'm still getting set up here. Don't know.
Applied abstract algebra. Is that just an oxymoron?
No, it's not at all. I mean, it's actually there's there's a ton of applications, but it's sort of the problem is the applications are very advanced. Like they're in areas that are much more advanced than an undergraduate, like a first undergraduate math course. So like if we were talking about, you know, quantum groups or something like that, then, you know, but you need some graduate physics and graduate math to like to start talking about that stuff. Yeah, there's a lot of applications from a string theory, you know, but of course people will argue that string theory has no application.
Argue that anything is their application.
Well, and I get it a lot. Very strange.
It's the worst part of it.
Well, this is the thing, is that mathematicians, we really have to like deal with it. Like, it's not like, at least at a school like this, like you can, you know, if you're at a higher level school, they would just, you know, yell at you and tell you to get out of the room. But here you have to deal with it. And you have to, you know, you have to have something you can say. Because otherwise they're gonna like try to end your existence. Mathematician. These guys are out, they're gunning for math. But you know, you never see this in like, you know, you never go to, I don't think that anyone, like I have friends that are like in English or like in the music school, like that teach music. I don't think anyone ever goes and be like, what's the application of this poetry? You jerk. Like, what's your application? I never hear that. I don't think they ever have to deal with that. Like,
I'm sure they do. I'm sure
you think
it's
they
just
do?
like, I'm sure the general public thinks math has applications more so than
That's the only reason.
I think. I mean, they do. I'm sure, but I'm sure they just accepted it.
Um,
People are still holding out hope that random math will help them.
Random math will help. Well, it does help. Well, but so here's my thing though, you're like, right? We've got all of this, like, by the way, group theory is certainly present, and knot theory, which is, you know, topology stuff, is very present in like the study of DNA and sequencing, gene sequencing. So like as a byproduct of all of our theories with DNA, partially using group theory, we have a vaccine to like deal with this. But now we have like half the people won't take it. So like the people that want applications still want to take vaccines. I don't understand what's going on. Like, what do you want? Here we like help make the cure for like a major pandemic, but now no one wants to take it. Really strange. I found that really strange. I was so excited
I know.
when the vaccine came out. I was like, yes, we're done with this. The cure is here. And then everyone who's like yelling about this stuff is like, well, I don't want that. I don't want the cure. Me cure. You're trying to kill me. What is going on? People want this to continue. I hate people. Worst people are just the worst. Take your medicine. Anyway, I could go on a rant about that all day long. I might do it at some point, but I'm not gonna do it right now. It's funny because like we have this thing, oh, I might do part. So we had this thing where, you know, like everybody has to be vaccinated, like in this, at the university, if you work here, or else you're fired. We can't ask people if they're vaccinated. Which is just like, what are we gonna do? Like, I mean, all the graduate students are employed here. So how do you like?
I had to upload a proof of my vaccination.
I know, everyone's got, right. Oh, we know how you have to do it if you're working, but it's more like from an administrative level, if you can't ask people whether they're vaccinated, like how do you, I mean, you can send them emails, but graduate students, half of them don't check their emails. So it's like, what do you don't want to invade their privacy and go in and say, hey, everybody go get vaccinated, because that's somehow offensive now. Come on. Anyway, whatever your personal choice is, let's do some math.
I had trouble with 3-1. I don't know if Nathan on there has anything.
Hey, Nathan, can you hear us? We can't hear you.
Yeah, I can hear you guys.
Do you have a
what
question?
problem did you say?
Yeah, I can hear you now. What did you say?
Okay. I was just asking what problem. It was just requested.
Sorry, I'm in the wrong class. What, do you have a problem that you'd like to look at?
Did he say 3.1 or 1.1?
Yeah, I did.
3.1, okay.
Yeah, let's do that.
Okay, let's do that. Thanks. All right. 3.1. So I haven't looked at any of these. I have to look, see what they are.
I think it's just it's new and we just did it today.
Yeah, it's good stuff. All right, 3.1. Yeah, we just did it today.
I think we hadn't really any chance.
You know, I really just want to get up to like section 5, I think, in this course. If you guys read this chapter, Artin gives you an idea of like just how, shoot. Sorry, I put this in the wrong lighter here. Gives you an idea of how like mathematicians, feel about their work. At some point, like he starts saying, he asks the reader, "Isn't this beautiful?" Which I just loved. I mean, it was just the best thing to read in a math book. You shouldn't ever ask that question, because as a mathematician, you haven't talked to enough people if you ask a question like that. You haven't experienced enough rejection. People saying,
Well, in a book, you can't get rejected.
that's right, in a book, but you should hear, the millions of people that you hope would read your book saying, no, it's definitely not, and I don't want to see. And maybe, but hopefully you get the percentage that will say yes. Okay, so 3.1. Alpha is an element of R, which is in this ring we're studying. And let gamma equal 1/2 alpha plus alpha times delta. Under what circumstances is this lattice with basis alpha gamma an ideal? Okay. So there is a lemma, I believe it's a lemma in this um, in this section that says when certain lattices are ideals and when they're not. So let me point to that lemma and copy and bring that over, and I'm sure that'll help us significantly. No, not this. Here. Not a lemma, proposition. But yeah, I'll bring it over. So if we look at this, this tells us which lattices, what a lattice needs to satisfy in order to be an ideal. So it must be, in order to have an ideal, you have to be a lattice, a sublattice, because of the ring of integers, because you're an additive subgroup. But then you also need to satisfy this extra property. Now it depends. So this extra property depends on the congruence of D mod 4. But we're in this case of D equaling -5, which means that in this case, D is congruent to 3 mod 4. Take some high level computation.
So why is mod 4 used everywhere? Like I see that, like why are we using mod 4?
So why, so Kale asked, why are we using, I'm repeating because it's like something Mike doesn't pick up. Kale asked why we use mod 4. And the reason is because, we have this result about, we are studying this ring of integers here. And so the ring of integers is one of two things. So in one case, here, I'm gonna actually use this thing I did last night. That was a gymnastic. I don't know why it was important for me to get the scaling right, but it was. So given any D, any negative, so given, this is just a comment here. Given D less than 0, D is an integer. And considering Q of the square root of D, we have this ring of integers R inside of it. So we know that, so we didn't prove that actually in class. We didn't prove that this was a ring. We defined the set of algebraic integers, but we didn't prove that it's a ring. But it's not hard to prove it's a ring. So that's kind of the thing. Actually, it's kind of harder than, in general, it is a little harder, but okay, it's not too bad. Well, actually, in general, it's not hard at all, but you have to do it right. Let me just say that. So anyway, we have this ring of integers, and now Kale's question was, what about mod 4 is going on here? So the point is that we had this result. Once we know it's a ring, forget about the case where we have here. We can call this 1. Oops. We call this 1 all the time, and we can call this delta. Okay. And so delta may be smaller. You may have to shrink delta down a bit, or maybe it's longer, depending on what D is. But if the point is that in this case, this is the picture we have. Literally, like, it's not metaphorically the picture we have. Up to that kind of scaling of delta, it looks like that. That's the ring of integers. As a subset of the complex plane, that's what it is. It's a set of points in that lattice. Okay. If D is congruent to 2 or 1. On the other hand, if it's not, then it looks different. If it's congruent to 1, it looks like this. Sorry about the 5s and so on. Take your your delta and you divide it by 2 and add it to 1/2. So here's delta, and here's this is what we call eta. It's 1/2 of the sum of these two. So these two things look different, and they are different. They're different, like as lattices. One is not similar to the other. In other words, I can't multiply and rotate one to get to the other. They're different lattices in kind of that sense of the word. Whereas these lattices all look the same. I mean, they're all just scales of each other. So they're all similar. So this is why we have this mod 4, is that these rings split up into two different possible situations, these rings of integers, depending on the congruence of our number D mod 4.
It's 0 mod 4.
0 mod 4 is left out because we want D to be square free. If D has a square in it, which is allowed, you can just take it out. You're taking the square root of D. So if I chose D to be like, negative, if I chose D to be negative 45, and I'm taking the square root of this, well, that's equal to 3 times the square root of negative 5.
45 mod 4 is
No, I'm saying, no, that's true. I'm just illustrating the why we want it to be square free.
yeah.
So we want it to be square free because we don't, this is not, there's no reason to have a square in here. If we're going to take A plus B times this, well, then by subtracting, I mean, yeah, we don't want these extra multiples in this component, essentially. Is what I'm saying. But 4 is a square. So 4 divides our number D, then we can pull it out.
Like 4.
4 is 2 squared
Why do we care about 2 squared?
because it's a square. We want it to be, you asked why, okay, you asked why not 0.
Yeah.
So there's two different questions. Why 4? And then why aren't we considering D congruent to 0? Those are two separate questions. So let's take the second one first. We're not considering D congruent to 0 mod 4 because we want D to be square free. And if D has a factor of, if D is congruent to 0 mod 4, then D is divisible by 4, which means it has a square factor. So it's not square free. Square free. Okay. Let me just make sure, because I've had people ask this.
It has like another prime square factor.
Square free, what does that mean? D square free means D is equal to, well, all integers are plus or minus product of primes. But here you want these to be distinct. That's what square free means. So in particular, D is not divisible by 4 because you would have 2 times 2 in that factorization. So that's why we're not considering D congruent to 0 mod 4. Does that answer that question?
Yeah.
Okay. Now, why is D 4?
Yeah.
I don't know. Ask God. I don't have a real,
There's more of an
stake on that.
observation, or is it just like-
well, it's this theorem that we have two different situations occurring with our rings of integers. One situation is this, it looks like that. The other situation looks like that. And the only way we can distinguish them is by looking at D mod 4.
How do we come to that? Is that just like an observation that was made, or is that?
Well, yeah, it's an observation. It's people noticed it. I mean, these are very natural rings to study if you're studying subrings of the complex numbers. I mean, these are very natural. They're just like, take one, square root and add it and see what you get. Like instead of taking square root of -1 for I, take the square root of something else.
What happened if we did like mod 9?
What's that mean? What happens if we do mod 9?
Like, why, like, what would happen if we chose something? that's-
All right, hold on. Nathan is probably like, like
Sorry.
throwing tomatoes at his computer screen. And I want to like, let me
Oh,
make this, I'll answer all possible questions that I can within the hour.
Sorry.
And then, but let me try to deal with this problem here. And so what I want to say is that this proposition is particularly relevant to this question. And the reason for that is, well, it gives us a way of saying whether a lattice is an ideal. So it says, under what circumstances is this lattice with basis alpha and gamma an ideal? Okay. So I'm going to bring this down. So according to this, so we're in our number D is -5, which is congruent to 3 mod 4. So we're in this setting. So this lattice here is going to be an ideal if and only if when I multiply it by delta, I'm contained within the lattice. Okay. Let's just explore and see. So we can say alpha gamma ideal, let's call it A. A is a strange letter to use for an ideal, but okay. If and only if by the proposition. If and only if delta times A is contained in A by proposition. So how can we verify that? Okay, well, we can verify it by saying that delta alpha and delta times alpha and delta times gamma are both linear, integer linear combinations of alpha and gamma. This holds. Only if delta times alpha is equal to, let's say A times alpha plus B gamma, sum A and B. Yes, no. Think this a little bit more. I think that this should be sufficient. So this should be sufficient. I'm not quite sure. So let's see. So maybe not. Maybe not. So, okay. I'm going to say what I need to say, and delta times gamma is equal to, let's say, C alpha plus D gamma. These are both, all of these 4 elements are integers. So we would need to show this if we were to apply this proposition.
What do we need the second one?
Huh?
Why do we need the second?
Well, you need, so that's I mean, you need to say that gamma, we're multiplying the whole lattice by delta. So we want to say that this is contained in the lattice, but gamma is in the lattice, and alpha is in the lattice. So anything like that. That's what we would need. So-
Good question.
Yes, please.
So I'm getting a little confused because there's a delta in the context of the problem, and then there's another delta in the context of the proposition. So
I
like,
think the same delta. I think
okay,
it's the same delta.
it's the same delta because that I think
Yeah.
D is usually the one in the brackets, not delta. So I don't know. In the proposition, what is delta referring to?
Delta, I think is this, delta, I think, is always equal to the square root of D.
Oh, okay.
I think that's notation, I think Art fixes in the beginning. Kind of the first or second section. Eta is this other element. So this eta here, that's this other element, 1/2, 1 plus delta, which is not present in this case of D equaling -5. So, well, okay, so there's something to say maybe before maybe I got a little ahead of myself. I think I did by applying this proposition, because I think we can sort of say something before we say this, which is we want to ask, they ask under what circumstances is this lattice an ideal? And I want to use this proposition, but in order for me to say that, I need that this lattice is actually a subgroup of R. And in particular, I need that gamma is an element of R, which is not always the case. In particular, I need that alpha times 1 plus delta is divisible by 2. So that's one thing that is not always the case. So we need, so in order for gamma to be an R, you have to have alpha times 1. Well, I guess alpha times 1 plus delta is divisible by 2. In R. But you could say in anything you want. I mean, let's just say in R. But it means that there's, okay, but maybe this is well, we can actually, maybe it's worth just going ahead and kind of writing this out a little more to see what it means. Maybe we get a restriction here. So alpha, so certainly if alpha is just an integer, it means that alpha is divisible by 2. That's what we start with. But in general, I can say alpha is x plus y times square root of minus d. And so what this is going to say is that, so what is alpha 1 plus delta? This is going to be x minus, sorry, this is x minus 5y plus x. Tell me if I'm doing something wrong here. I think I'm okay. Yes. It's supposed to be a 5.
On the Y.
This is also supposed to be a 5. I'm multiplying. So I'm not, my handwriting is horrible. Remember, delta is square root of negative 5. So this actually tells us something right away. So then this is something maybe we should have noticed. But you can now tell me what this, Nathan or Kale, tell me what I've learned here about alpha.
How?
Huh?
Alpha is necessarily either alpha or 1 plus delta. But since 1 plus alpha, delta can't be alpha. Sorry, alpha is divisible by 2.
Yes.
I think that's a good.
No, alpha is not divisible by 2, not necessarily divisible by 2.
But if
This is the problem, guys. Okay, I'm using you as an example here. All of our arithmetic doesn't work. All of our understanding of how things are supposed to work, it no longer works. We're in Z, we're not in a UFD anymore. Alpha is not divisible by 2. Alpha times something else is divisible by 2. And that other thing is not divisible by 2, but the product could be divisible by 2, even if alpha is not divisible by 2. We don't have unique factorization. We can't use the normal naive things that I'm not calling you naive. I'm just saying the things that we're used to using. Our intuition is wrong. You have to be much more careful in this world. And so that's why I'm writing this out, is to say, okay, what do we know? And versus what do we not know? Big shot at Nathan? What can I say?
Um,
Correct. So one thing you can say is if I have a number like 5, like let's say 7, and it divides A plus B times I, right? Or it divides A plus B times the square root of minus D. If I know, then I know it divides A and it divides B. That I know. If I have an integer like 7 and it divides a given, then I must divide both of them. Because just looking at what multiplication means, I'm 7 times another number, it's going to be 7 times the real part, what's 7 times the, So that's just, so if it divides something, then it has to divide each of those two guys. So what I'm saying is that 2 divides the product, 2 divides this, and I just expanded the product. But that means that 2 divides this and 2 divides that. So if 2 divides this and that, what can you say about X and Y? X and Y are definitely integers. So we are in this case. We are in this case. So the ring, good. Parity. What can you say about X and Y? They're both even or both odd, which means X is congruent to Y mod 2. That's an equation that you can say. Now we've seen that equation. I wrote that equation. I'm the only one who's ever written. I wrote that equation today. I wrote that equation to describe that ideal. That was that red checker ideal. That was in, and so this is saying actually that alpha is in the ideal that we're discussing today. Alpha is in the ideal. As you'll recall, that ideal was generated by 2 and 1 plus delta. 1 plus, yeah. That was the ideal. So we get something. Without having to even apply the proposition yet, we get this. So now, and that might help us here. So that might help us. I don't know if it will. We'll see. Now I have to think. All right, so now I'm trying to be clever here. To see if sure there's something clever here. I'm not.
I looked at that two, the X, we would fill into Y one, two, do we establish the two comma? Is that an ideal? Like, is that?
Yes, that's in the, I don't think we proved that, but this is something that is, it's very easy to prove. Using the proposition, you multiply both of these by delta, and you can see that these are both going to then be in this class. But I don't want to prove that right now. I can, that's not hard, but I don't want to do it right now. But maybe actually the proof of that might be helpful for what we're trying to do here. Maybe not.
We then prove the same thing for gamma, and then if both were an ideal, basis also be an ideal?
Yeah, maybe we should try this. Maybe we should try, let's take a look. So now that we have this information, let's take a look here and see if we can't say something. Let's just, so delta of gamma is going to equal delta of 1/2 alpha plus alpha delta. This is 1/2 of delta alpha minus 5. Oh, minus 5 alpha. And so I want to say, okay, well, let me do the usual thing. It's delta alpha plus alpha, right? I add, so I have to take away minus 6 alpha. That's pretty good. Do you agree?
Oh, yeah.
Really?
Yeah. Okay, no, sorry.
I never do mine. It's a real asshole. Good. So, which is good? Which is, yeah. Actually, I don't think we needed anything for this. This we got. So this is satisfied. Okay. What about, I feel like we should then also be able to do this somehow just by being kind of silly. So are you with me? So C is 1, or so D is 1, start D. I don't want D here. Call it E. So E equals 1. C equals minus 3. On integers that do it. Huh?
Could we just do the same thing for alpha?
We're going to try. We're going to try. So delta alpha. So yeah, I think we can do the same thing here. Yeah, because this is pretty easy now. This is 2 gamma minus minus alpha. Am I just silly?
Like, is that the final? Is that you're saying is the final form? That you just
I don't know about final form. I just know that I can find, and so
Those are A.
A equals -1 B. Yeah, this should be unique because it's a basis, but presumably, but okay. Oh, too bad. I might have to, let me run upstairs in a second. Let me just finish this argument. Okay. That'll work. So actually, we can do this without any of this argument up here. However, we really did need to do this argument up here to make sure that the lattice that we had was actually a sublattice of the ring of integers. So this was important, but then once you have that alpha is in here, you do indeed, you can use the proposition to say any alpha in here will give you such a lattice. I believe I want to say that's true. I think it's okay. It's okay. So the answer to this is really alpha has to be in the ideal. The ideal, this kind of prototype ideal.
So it has to be in 2, comma.
Yep, has to be in that red checkered ideal. Those are the ones for which we get an ideal. Otherwise we don't. And it's really more, it's not really about it being an ideal, it's about it being an algebraic integer. Once you get that, then you have to verify this and use the proposition. Are there more questions? I've got like 5% on my battery life. So I've got 5% of questions left.
I would defer to Nathan.
Nathan, you're being deferred to.
Yeah, I think that's the only question I had, for the sake of your battery.
Okay.
I mean, I actually didn't have any more
My
questions.
iPad thanks you, as do all the other students in the class.
Thank you for your help.
All right. Okay, then I'll conclude this, wrap it up, and wish you all luck for the rest of the problems. Okay.
Did you say when the final is going to be?
I'm gonna get this, I'm gonna write this up this weekend and I'll have it posted. I don't want to say by class time Monday, but just sometime Monday I'll post it and I'll give you plenty of time. So you'll have at least a week and a few days, maybe even like closer to a week and a half.